Okay, so I'm recording here, of course, and so we're continuing now talking about our section 5.9 approximate integration. And here is the integral from 1 to 2 of e to the 1 over x power dx. And this time I want to know, I want a certain accuracy. I want to know how many subintervals would be needed to guarantee that the midpoint rule approximation for our integral would be accurate to within 1/10,000th. Okay, so now what I'm doing is, rather than just saying, oh, let me use 10 subintervals, let me use 20 subintervals for my approximation, I want to figure out ahead of time how many subintervals we will need to use to get an approximation with a desired accuracy. And you might notice that 0.0001, okay, this level of accuracy, okay, when we use 10 subintervals to approximate this integral with the midpoint rule, you know, based on 10 subintervals, we were guaranteed that the error in our approximation would be no more than 0.0003398. Okay, we were guaranteed that. Now we want to have a bound on the error that's smaller, 0.0001. So do you think the number of subintervals we're going to need to use is going to be more than 10 or less than 10? Based on the accuracy, the increased accuracy that we want.
More than 10, probably. Yes.
That's exactly right, Shalom. Shalom. Yes, more than 10. Okay, the question is how many? So this is important. You know, for instance, if you're doing computations, if you're trying to find out the number of subintervals, the number of subintervals is going to determine, for instance, how long your computer runs to get the approximation. Now, computers are pretty fast, so it might not make a big difference whether on the number of subintervals, but if we're talking, you know, 10 trillion subintervals, you know, there that might be important information for a computer scientist to know. How many are computer science majors in here? I know we have some. Okay, Mark is, Masume, Daniel, say it. Sadid, Franklin. Okay, good. Well, okay, so here's what we do. We're going to use the error bound formula again. Here we are, error bound formula. So the bound on the error is less than or equal to k. So we don't need to redo k. We already found k, that big value of k from before. Okay. And then 2 is equal to b. 1 is equal to a. And but now we want to determine what n is. So if we require that our error bound be less than 0.0001, this will then ensure that our error is less than 0.0001. And so what happens is we have an inequality to solve for n. And the inequality, based on here, the error bound formula, is 3e over 24n squared is less than or equal to 0.0001. I want to solve this inequality here for n. Okay, and so I'm going to do that. All right, I want to get the n squared up. I want to make this inequality a little simpler. So I'm going to multiply both sides of the inequality by 24n squared, because then you get simplification here and just 3e on the left. But on the right, you get 0.0001 times 24n squared. Again, we want to solve for n. We're not done yet. Why didn't by the way, don't with inequalities, when we multiply through by numbers, sometimes we have to worry about the sign switching, right? About the inequality switching from like less than or equal to greater than or equal, but we didn't have to do that. Why is that? When we multiplied by the 24n squared, when we multiplied through the inequality by 24n squared, we didn't have to worry about the inequality sign switching. Why is that? That's right. Good. Good. 24n squared is always positive. That's right. So the inequality will not change. Okay. So all right. Well, now we want to solve for n. So naturally, what I'm going to do, let's see, Jonathan, assuming n factorial. We'll talk. Hold that thought. So I'm going to divide both sides now. I'm going to divide both sides. Oh, come on now. I want to get this to go right. Yeah, I'm going to divide both sides of the inequality by 0.001 times 24n squared. 0.001 times 24n squared. Okay, so I'm dividing here. And that's positive also. So the inequality sign doesn't change. You got simplification here. No, I'm sorry. I don't want the n squared, right? Let me do this again. I'm getting, I don't want to divide. Hold on, let me do it again. 0.0001 times 24, right? 0.001. Sorry, 0.0001. One moment, everybody. Now I'm just going to take a little breath here. Right. So, all right. So then we get some simplification. And so n squared then is greater than or equal to 3e divided by 0.001 times the 24. And take the square root of both sides, and then it's greater than or equal to the square root of that. And if we compute 3 times e divided by the denominator, 24 times 1/10,000th, you know, if we take the square root of that, we'll get 58.29. So n has to be greater than or equal to 58.29. So the question is, how many subintervals do we need? Do we need 58 subintervals? Or do we need 59 subintervals? Algebraically, that's right. Good, Jonathan. We would need 59. Because yes, if you round n, you'll get 58. But 58.29 rounds to 58. But n is an integer. It's the number of subintervals. So you can't have 58 subintervals is not enough. You need 59 because 59 is greater than 58.29. Please let me know if you have any questions. Okay, well, then it turns out then that we would need 59 intervals to achieve an accuracy of 1/10,000. So essentially, n for this problem, n subintervals. Okay, and I should probably write subinterval, right? Here, subintervals. With 10 subintervals, we were guaranteed an accuracy of about 3/10,000, a little more than 3/10,000. But if you wanna get that accuracy down by 2/3 to 1/10,000, you gotta increase your number of intervals by like 50 subintervals. You gotta increase it like 6 times. So it's kind of amazing, but that's how it is in math. If you want more accuracy, you gotta then you take more subintervals, but it's more than you'd think it would be, you see. Your new error would be guaranteed to be 1/3 of what it was with 10 subintervals, but you have to increase your number of subintervals by 6-fold, so to speak. So it's really a fascinating idea. And are there any questions on that?
Is it because the number is squared?
It has to do with the formula. Indeed, it does, Shalom. And I'm looking at that formula. Let's see here. I'm trying to think if there's a.
The x value gets squared in the denominator, right?
It does. It does. So the square does play a role. The square does play a role. I'm just trying to think if there's I'm just thinking on this. Hold on. Yeah, it's certainly interesting. Certainly interesting to be sure. I want to be a little careful how I answer that. Many times in applications, if you want a certain level of accuracy, you have to really increase your number of subintervals, like a lot. And it's just because to get more accuracy, to get closer to the truth requires a lot more subintervals. That's how I would think of it. That's how I would think of it.
Well, per each subinterval, there's a plus and minus, right? You have some increase and some decrease.
Yes.
And so therefore, like with that kind of like 2 steps forward, 1 step back type thinking, it would make sense that you would need more than you would think.
You know, I never thought of it like that. I never thought of it like that, Shalom. I'm gonna let me think on that a little bit, okay? Let me think on that comment that you made there. All right? Does that sound good? And then I'll get back to you on that,
Oh,
and
yeah,
maybe the
sure.
class on that. Yeah, I never thought of it that really that way. But excellent comment. Excellent comment.
Thank you.
All right, you're welcome. You're welcome. All right, I'm gonna stop the recording here.